In working with computers, there are three types of numbering systems that we use: the decimal number system, the binary number system, and the hexadecimal number system. It looks very strange when you're not used to it, but thankfully these numbering systems all work in a very similar manner to what we're already used to. So let's take a look at the decimal number system to start off with. Here's an example decimal number, 213. We can work with numbers as large as 213 or even larger by the use of different things such as the ones place, the tens place, and the hundreds place. We're not stuck with only the numbers 0 through 9. So by using the tens place, we can add in at least another 10, and by using the hundreds place, in this case, we're adding in another 200. So we have 200 plus 10 plus 3 for a total of 213. When we count, we can see this in use again, because here we'll start off with the number 007. I've left in the leading zeros to sort of show the example of how these hundreds and tens places still exist, even if they're not always written. So we've got number 7. After the number 7, we've got the number 8. From 8 on to 9. And once we get to 9, we've got a little bit of a problem. How do we go beyond 9 since we don't have a digit that goes beyond 9? Well, we use the tens place. We reset 1 back to 0. And we use the tens place and increase it by 1. Alright, this is the counting system that we're all familiar with, and thankfully binary and hexadecimal number systems work the same exact way, except they have a different number of digits, not just 0 to 9, but they have a different number of digits that they work with. Binary number system. The binary number system only uses 0 and 1, no 2, 3, 4, or up to 9. So this makes things a little bit more complex than what we're used to. Now, in this case, since we can't go all the way up to 9, we don't have a tens place. What we have is a twos place and a fours place. So, counting works something like this. The first one, we go from 0, we go to 1. We've got a 1 in the ones place. Nothing terribly different there. But we can't go from 1 to 2 because we don't have a 2 available. So we have to reset the 1 back to 0 and then move an item into the twos place. So at this point, what we've got is 2 plus 0 equals a total of 2. So we've got 1, 2. And no ones, so we have a total of 2. We count to the next digit. We've got 1, 1. So what we've got is a 2 and a 1 for a decimal value of 3. Next one, we can't do anything more with the 1 and 1, so we go ahead and move the 4's place up to 1 and reset these. Now we've got 4 plus 0 equals a total of 4. What's the next number? Well, we want to get up to 5, so we want to add 1 to the 1's place. Then we want to get up to 6. So we go ahead and reset the 1 back to 0 and add 1 to the 2's place. So now we've got 4 plus 1 is equal to 6. And hexadecimal numbers. This goes the opposite direction, and instead of having less digits to work with, we have more digits than what we're normally used to with the decimal number system. The hexadecimal number system, we've got a 1's place, a 16's place, and a 256's place. So this is a decimal value of 8, a decimal value of 9. Now, what we're used to is the 9 will go down to 0 and it'll have a 1 in the tens place. That's not the case. Here we use the letter A to represent a 10. B, C, D, E, and F represents a 15. Now, at this point, we've used 0 through 15, a total of 16 different combinations, hence the word hex. So we've got a hexadecimal place, and we've got a total of 16 different combinations. So if we run out of letters, we move a 1 into the 16th place and reset the 1's place. So a 10 in hexadecimal actually represents 16 in decimal. We can take a look at this table to get some different examples. Binary 1 is equal to a decimal 1, which is equal to a hexadecimal 1. A binary 10 is equal to a decimal 2 and a hexadecimal 2. Binary 1000 goes to an 8 and an 8 in decimal and hexadecimal. 1111 is a 15 in decimal and a hexadecimal of F. Now this is actually kind of nice in that each grouping of 4 binary numbers is one hexadecimal number. But that's not the case with decimal. That's one of the reasons we use hexadecimal, because it translates very easily from binary to hexadecimal and back, but going back and forth between decimals is a lot more complex of an operation. So 10000 is a 16 in decimal and a 10 in hexadecimal. 11111111 is 255 in decimal and FF in hexadecimal. So going one beyond that, we reset the hexadecimal to 100. 256 is a value in decimal, and we've got 1 along with 8 zeros for binary. So that's your introduction to the binary, decimal, and hexadecimal numbering systems.